So we've learned that chemical reactions can be exothermic, giving off energy, or endothermic, absorbing energy as they occur. The amount of energy can be quantified with a function called enthalpy. So the enthalpy of the reaction, which is given the symbol delta H reaction, is the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. So there are a lot of details around this that we don't have to get into, so we can be thankful for that. So the word is enthalpy. You should know, if that's used in a sentence, you should be able to figure it out. We can really think of it for our purposes as being heat, and yet it's not exactly the same thing as heat. So delta H. If we think about it, if you burn a cigarette lighter full of butane, or you burn like one of those big tanks you see outside of houses in the country, if you burn that amount of butane, is there going to be a difference in the amount of energy that's released? Sure. If you burn more gas, you get more energy, right? That makes sense. So we can calculate how much energy is given off. I got ahead of myself. The sign of delta H. So the sign of delta H can be positive or negative, and it just indicates the direction that the energy flows. We've talked about this before. It's a lot like money. So if I pay you $5, then on my account for my bank, it's going to say -5. On yours, it's going to say +5 because of the direction that the money went, right? The same thing with the enthalpy, the heat. Energy going out of the chemical system is negative. It's a withdrawal from the account. Energy coming in is positive. It's a deposit. So in an exothermic reaction, the reactants start out with high energy. They release energy, and the products have a lower energy. Delta H is negative because energy went out from the system. It goes into the surroundings. In an endothermic reaction, the reactants start with a low amount of energy. They have a positive delta H. Energy comes into the system, and the products end up with a higher energy. Where did the energy come from? It came from the surroundings. So many times an endothermic reaction will get cold, and it gets cold because it's sucking heat from the surroundings. So delta H is negative for exothermic because the energy is leaving. So here's CH4. That's methane. It's the main component of natural gas. When you burn natural gas, energy is released. So we can add on to our balanced chemical equation the heat of reaction, the enthalpy of reaction equals minus 802.3 kilojoules. The negative tells us that's being released. Well, how much methane is burned to give you this much energy? It's the amount indicated in the chemical equation expressed in moles. So 1 mole, there's an unwritten 1 in front of CH4. 1 mole of methane, when it combusts, will release this much energy. Why is it that way? Why is it this much for that many moles? Because that's how they decided to write things. Okay, so we just have to get with the program and do what everybody else does. Sometimes you have to do that. 2 moles of oxygen are consumed when that reaction occurs. 1 mole of carbon dioxide is released, 2 moles of water are formed. So in the formation of 2 moles of water, by this process, this amount of heat is released. For a positive delta H, you have an endothermic reaction. Nitrogen and oxygen will react to form nitrogen monoxide. When that happens, energy is absorbed from the surroundings. So when 1 mole of nitrogen reacts with 1 mole of oxygen, 182.6 kilojoules of energy is absorbed from the surroundings. So this number, delta H, it's an amount of energy that relates to the molar quantities in the balanced chemical reaction as it is written. Mm-hmm.
Like the number
Mm-hmm.
of the positive 182, how did they come up with that number?
How did they come up with this number? That's a great question. There's a variety of ways. One of the simplest, like with this one especially, one of the simplest ones is to burn a certain amount of methane and measure how much heat is released. Yeah. There are calculations that can be done, but basically it's by experiment. They just did it and figured out how much. There's no way that you look at this and do something just looking at these in the periodic table and figure out what this number is.
So we're not going to have to figure out
No, that would be given to you. Yeah. So this is good. Is sometimes when students ask a question, I think I might know what's really behind the question, but sometimes I don't. So the question is, do I have to know that, and how would I know that? No, you don't have to know that. There's no way you could know that. I don't know that off the top of my head. I pretty much don't expect students to remember anything that I can't remember. Right? If I do this for a living and I can't remember how many kilojoules of energy I released in the formation of 2 moles of NO, there's no way I'd ask you to do that. So we specify delta H reaction in combination with the balanced chemical equation. So the magnitude of that is for the stoichiometric amounts of reactants and products for the reaction as written. Now, the reaction could be written with coefficients that are not in the lowest ratio. It could be written with coefficients that have fractions. It's okay. You just do it however it was written. So let's look at this one. So here is combustion of propane. That's the fuel in LP gas. So here's propane. When it burns, it combines with oxygen. It forms CO2 and water. And when 1 mole of this burns, it releases 2,044 kilojoules of energy. So this much energy for 1 mole of this. This much energy for 5 moles of water. This much energy for 3 moles of CO2. This much energy for 4 moles of water. So we can convert between energy and moles of anything in the chemical reaction in one step. We've got a whole bunch of possible conversion factors that we can write from this. So we could say, well, there's 1 mole of C3H8 per 2,044 kilojoules of energy. Or there's 2,044 kilojoules of energy for every 4 moles of H2O that are formed. That's a good question. What about the negative? I kind of go back and forth on this. Let's write the negative. So go ahead and use the negative. I think that's the least confusing in the long run. Remember that the negative just tells us the direction. Okay? So any questions about how you would write or make conversion factors from an equation with a delta H? You can relate this amount to any reactant or product. Very convenient. So let's look at this. Here we have ammonia reacting with oxygen to form NO and water. Delta H is negative 906. So the negative here tells us that that's the amount of energy released. It's an exothermic reaction. So this is saying calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So this is a stoichiometry problem, but it's got energy involved. So the normal thing for stoichiometry was grams to moles to moles to grams. And that always should be the starting point. But sometimes we modify one or both ends. So let's look through this and see what the numbers are. Okay, 155 grams of ammonia. Well, let's write that under the symbol for ammonia. 155 grams of that. Calculate the heat. Well, this is the heat term. So I'm going to put the question mark over here, and the unit requested is kilojoules. And I think, okay, grams to moles to moles to grams. I've got grams to start with here, right? But I'm not going to end up with grams. I'm going to end up with kilojoules. So I'll cross off the gram thing. I'm going to go grams of ammonia to moles of ammonia. Do I need to go to moles of anything else? No. Because this tells me that 906 kilojoules of energy are released when 4 moles of ammonia react. So I can actually get rid of that mole term as well, and I can go straight to kilojoules there. Because I have this relationship between kilojoules and moles of ammonia. So 155 grams of ammonia. I'm going to convert to moles of ammonia. And then I can go straight to kilojoules of energy. So getting my units to work out, I put grams of ammonia down there, moles of ammonia down here, and I see that I'm going to get kilojoules. So this is the relationship, this is the amount of energy for 4 moles of ammonia. So minus 906 kilojoules for every 4 moles of ammonia that react. And then here I need the molar mass of ammonia, which we've used before, 17.034. So I've got 155 divided by 17.034 times negative 906 divided by 4 equals. So this should have 3 significant figures. So negative 206, there's my third significant figure, write down 2 extra digits, 1.0 kilojoules. When I go to round this, here's my 6. I'm going to keep the 6. The next digit is the decider. It tells me that I keep this as a 6. So I've got negative 206. But I have a place here that I'm dropping before a decimal point. I need to replace that with a 0 so I don't change the magnitude of the number. So negative 2060 kilojoules. A better answer is negative 2.06 times 10 to the third kilojoules. Any questions? Let's do another one. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And a second question, what mass of carbon dioxide is produced? Well, let's just deal with the first one. Well, what are we given? We're given an amount of heat. 1.5 times 10 to the third kilojoules. This is the heat term, so I'm writing that down over here. And the question is mass of butane in grams. Well, this must be the butane because I know what all those other things are. So question mark grams. This 13 halves might bother you. It's a fraction. What's it doing there? This number is for the molar quantities as written. Don't worry about it. It's okay. Our general path, grams to moles to moles to grams. We're going to have to switch it up here because we've got energy. We're trying to find grams this time, right? So we're going to keep the grams, and we're going to have to keep the moles, but we're not starting with grams. And because of this relationship that we know kilojoules per 4 moles of this, we don't have to go from moles of one thing to moles of another. We also don't need that. And so we can just start with kilojoules and go directly to moles of whatever we want. Everybody okay with that? Sometimes you try to go moles of this to moles of that to moles of that to moles of that. Well, you can get there, but it's kind of a long way. Okay, so 1.5 times 10 to the third kilojoules. And I want to convert to moles of butane, because that's where the question is. C4H10, and then I want to get to grams of that. So I put my units in here so they cancel out. So this term relates moles of butane, so it's 4 moles of butane, to the energy, which is negative 2658. And then I need a molar mass, so let's do that. 4 times 12.01 plus 10 times 1.008. So 58.12. grams per mole. Okay, so 1.5 EE3 times 4 divided by negative 2658 times 58.12 equals 2 sig figs this time. There's my 2. I write down 2 more grams of butane. What's wonky about that? Can you have a negative mass? No, you can't have negative mass. What happened? Well, this is where the signs can be a bit confusing, okay? Let's think about this starting amount of heat. Producing this much heat. Is that being released or absorbed by the reaction? It's being released. So that really should have a negative in front of it then, right? So if we say negative, well, now we've got 2 negatives and this becomes a positive. That's the best thing to do. Kind of a shortcut is, when you're doing a problem like this, if you end up with a negative mass, just ditch the negative sign. That'll work too. So if I was going to round this, I keep the 1 and the 3. The decider is telling me that the 3 is going to remain a 3. And then I have to put a 0 there to hold the decimal place, because 13 and 130 are not even close to each other. Better answer, 1.3 times 10 to the 2 grams. Any questions? So there's another question here. What mass of CO2 is produced? There's a couple of different ways you could go about that would be fairly easy. You could do very similar calculation starting from the energy. Or, if you're more comfortable, you could take this mass, I would use the unrounded mass, you could take this mass of butane and calculate the mass of CO2, grams to moles to moles to grams. I'm going to skip actually doing that part of the problem because we're short on time. Any questions about this problem?
Can we say the first option?
The first option, just take the heat and instead of calculating how much of this would burn, calculate how much of this would be produced.
Oh, just with the conversion.
So kilojoules to moles of CO2, 2 grams of CO2. Whichever seems easier to you. So in the homework, the absolute value of heat is often requested, and words are used to convey the sign. So I'm just giving you a heads up about mastering chemistry. In this question, it says calculate the heat associated. Does that tell us a direction? That it's coming out or going in? No, it doesn't. If the words don't give direction, then you have to include the sign. If we have something like this and it's talking about calculate how much heat is emitted or how much heat is produced, given off, or absorbed, where the words tell you the direction, then you use the absolute value, you make it a positive. We do this with money. If I pay you $5, I pay you, the words tell who the money is leaving and who it's going to. We don't say, I pay you minus $5. It's minus for me, it's plus for you. Okay? Without words on your bank statement, you need a sign to show direction. But with words, you don't need the sign. Okay? There we go.